Well, I want to introduce this evening's speaker. We have three guests from the University of Washington, and as many of you know, out of courtesy, rather than wear cougar wear like you did, I actually wore satellite-themed. And I'd like to introduce Paige Northway, who is an Earth and Space Science graduate student pursuing her PhD. And Paige, I apologize, I didn't find out your piece on the aircraft.
I'm the propulsion.
Propulsion. Okay, so you're the one that's going to talk about the thing that most enthralls me. And Paul Sturmer, who is a physics graduate student pursuing his PhD. And Paul, my understanding, you're kind of partially responsible for the amateur radio aspects of the satellite.
Yep, so I helped integrate one of the radios from AMSAT that they provided to us, and then I also developed the 24 gigahertz beacon.
Okay, so really for once the original mission is completed, one of the things that the amateur radio community, at least the amateur satellite community, needs to keep in mind, we should be thankful for your efforts, correct?
If it works.
Well, I think for a lot of people, the try is just as important. And then last but not least is Nathan Wacker. Sorry, I need new glasses, so it's like, this is, well, I guess I could do that. Yes. There we go. He's a computer science undergraduate student pursuing his Bachelor of Science, also at the U. And your piece on this is?
I did a lot of work on the flight software as well as the ground station software, and I'm currently in charge of operations.
Neat, neat. So how about a warm round of applause for our...
Thank you. Paper with all this written on it.
Paper is so old-fashioned.
Are we ready?
Yes.
Thank you for the introduction. Just to put names and faces together one more time, we have a little slide to do that, and then if it is desired, we can potentially send this presentation out later. If people want to have a copy of it.
Yeah, we'd love that.
You will have that. Yeah, so CubeSats, I am not super familiar with your group. So is everyone familiar with the idea of what a CubeSat is? More or less how they came about? So we're going to throw a lot of CubeSat terminology around later. So this would be considered a one-use CubeSat. So it's approximately 10 centimeters by 10 centimeters by 10 centimeters, which is where you get the cube name. And so the CubeSat, even when you get into more of a 3U configuration, so you have approximately 3 of these stacked together, and it is no longer a cube, we still call it a CubeSat. And so that's where that terminology comes from. And the CubeSat, the idea is that it's a standard. So universities, groups can build things to a particular standard, and a single type of launcher can then deploy them, and that brings down the cost of doing these launches quite a bit. And you can see in the graph, since 2000 is when they really started launching CubeSats, and there's just been a lot of growth. And this only goes up to 2017, but 2018, I think, saw the most CubeSats launched. And then 2019 was a little bit of a slump, but they predict something on the order of a couple hundred once you include both university and private companies. Excuse me. The sort of poster child for private company involvement in CubeSats is Planet, which is a company out of California. They very briefly had an office in Redmond, I think, but nothing came of that. But they launched, I think, 300 CubeSats of approximately this size. Their Dove constellation, and they're doing things like imaging all of the Earth in very high resolution every 24 hours. So there's a lot of interesting applications that are coming out of even tiny satellites like this. The very first CubeSats that were launched were like Eversat. Like they'd go up and they launched and they make noise and everyone would celebrate. As time has gone on, a lot of things become miniaturized. The CubeSats are now doing real science, and not only just in low Earth orbit, but then also in cislunar orbit or going out to Mars. Some CubeSats that are about twice the size have been proposed to send, and some of them tested in not low Earth orbits. So CubeSats are really kind of an exciting thing in the space community right now, and the MSAT group has several that are up that they're involved in as well. I think that kind of covers what I was going to talk about there. So I can pass this around if anyone wants to see. This is just a 3D printed version of a 1U CubeSat. You guys can pass this around too. This is an actual sized model of HuskySat. Solar panels on the actual HuskySat don't deploy, but the actual HuskySat looks more like this. But these ones you can see kind of inside our board stack, and I'll talk more about that later. So the CubeSat team at University of Washington began as an offshoot of Professor Robert Wingley's Advanced Propulsion Laboratory. That's where Paul and I got started working on CubeSats. The propulsion system has been something we've been working on in the lab for quite a while, and the idea was we wanted to get it tested in space. Paul and I actually started looking into the technology that eventually became the 24 gigahertz radio and basically the format for the propulsion system by looking at trying to do something called the NASA Lunar CubeQuest Challenge, which is that idea of sending a 6U CubeSat into orbit around the moon and communicating back. And I'll touch on that again in a minute. But we didn't actually end up doing that, but instead we managed to get funding through NASA USIP program, NASA Undergraduate Student Instrument Program. And so that funneled us into the CubeSat Launch Initiative, which is where we were able to get launched with. So NASA paid for our launch, which was very nice. And the team, I think right now the team is composed of 30 undergrads and 2 grad students. Over the course of the whole project, we've probably had 60 to 80 undergrads who had a meaningful contribution to the satellite program. So it's been a really good learning experience for a lot of students at the University of Washington. And then, just for fun, I ended up putting together a timeline. We actually proposed the project through the NASA USIP program 4 years before the launch. And so that proposal happened, we got accepted following spring, and then they didn't actually have a kickoff meeting until almost a year later because we were working with NASA. And then once that kickoff meeting happened, they funneled us in the CubeSat Launch Initiative. We went through several review sessions and actually changed it from what you see there to one without deployable solar panels, and changed several things that we can talk about later. We delivered it, and I'll talk about this in August of this year. We took it down to Houston and put it in a box. It got launched into space in November 2nd, and then finally deployed on, that's wrong. January. Not January 20. January 31st of 2020. And just for a little kind of a fun thing, I thought our original proposal for that lunar CubeSat that was going to go to the moon and communicate back, we had budgeted ourselves, less than 3 years to deliver a very cool CubeSat. And so you can see kind of how our timelines and our project scope changed throughout that. But we were very optimistic throughout the whole thing. And so this is just sort of how the satellite got into space. We put it in a metal box, which we put in a Pelican case, which I then checked or carried on to an airplane. That was very exciting. I was really worried about going through security, and I had all these papers, and I was ready, and I had an ESD bracelet in case I could take out. Turns out there is no one in the airport at 6 on a Saturday, so trying to get someone to acknowledge that I have a weird thing that I'm taking, oh, talk to the next person, So I go to the X-ray machine, and I gently set it on, and there's 4 guys standing around because there's no one going through security. And I look at me, it's like, okay, I have a satellite. If you need me to, I can take it out of this box, but I can't take it out of the other box. What do we need to do? They're like, oh. Cool, just right through. And so I go over to actually go through the X-ray machine.
So if we wanted to smuggle 100 pounds of cocaine through, that's
Well, there's
essentially
not
told us exactly how to do it.
eyes on that X-ray machine.
A cube.
But that was the fastest I've ever been through security. And then so we installed the satellite in here, down in Houston. Then, and that was with called NanoRack. And then the NanoRack shipped the box up to Virginia. And that big white box, the kit on the box. So that box is where we rode to space. We were in there at the launch, and so this is the Cygnus capsule. At launch, we were in the VIP section. We were closer than anyone else, which still means that you're 2.5 miles away. And so you can kind of see right there. There's
This is Canaveral?
no, we were at Nessa Welps.
Okay.
Virginia. And yeah, so it was actually sort of really cool. Addie was there, asking him about it. You could still feel like the vibrations of the launch, and it was very exciting. But you got there and you're like, oh, there it is. I thought we were going to be a lot closer. But it was very exciting launch. And then we went into space. There's the Cygnus capsule, and again, there's our little box. So when the Cygnus capsule was docking with the ISS and they had the live feed, you could kind of watch it. You're like, oh yeah, there's the box. We're still in it. Looks good. And then finally, I had to get explicit permission to use this photo, but this is the box that we were in. And the door opened, and there were 2 satellites here, and then our satellite was here, all by itself. And you can see up in the corner, there's a HuskySat moving around. You can see the shadow on the solar panels. So that was pretty exciting when we got this picture.
They figured that aim out.
And it works.
So
That was sort of the scary part of this whole thing, is that because the Cygnus module was docked with the ISS, it went up into space and then sat at the ISS, I mean, for a couple months, was it? 3 months? And so it wasn't until the end of January, so maybe 2 weeks ago, that we finally got this thing deployed and got first contact with it. So everybody says, oh, was the launch exciting? And I'm here the whole time just crossing my fingers waiting for this thing to actually turn on and not just be a space brick. Very fancy space brick, mind you. And so on the 1st of February, we were able to make contact with it, and everybody was really excited. We got a lot of alumni back in the lab. So here's the photo. And we were finally able to hear it and confirm that all of our engineering, in fact, paid off. And one of the coolest parts for me, because you could hear it and you could see it, but the first cool thing to tell that it was really working is here's some data from a whole bunch of orbits of this satellite. And it's not necessarily important what these data are, but you can see the cyclic nature of this. You can see the battery charge, and the battery gets drained in the eclipse, it gets charged in the sun and drained again. And so we can see that this thing is healthy and that everything is maintaining itself across the orbits. And you can see, because they're slightly tumbling, that in eclipse nothing's being generated, but the panel power is all vary. And here we know we've built a healthy satellite, and we can continue with the mission. So speaking of which, we made first contact, and we just had a very small beacon on there, and the first step was we enabled continuous transmission mode. So if you're following the modes, that's sort of what we were doing today, and the mode that we commanded into, and when you see that little beacon is what we started out with, and then we commanded into the health mode and get continuous data. And then after that, we commissioned the power system to make sure everything checked out. And I should mention, by the way, the fact that we're able to get such fantastic data was not just through our station. Because of our partnership with AMSAT, which I think Paul will talk a bit more about later, we were able to leverage data from all the other AMSAT stations that are uploading to a common server. And so in that way, we're actually able to have, through the amateur community, a whole network of ground stations at our disposal versus ours. So, I mean, if we would have just seen a very faint signal, we might not have known anything, but through that, we're able to really paint a very good picture of the health of our spacecraft. Anyway, so we commissioned the power system, and we confirmed that everything was good. We saw the battery was charging. We saw that we were getting a nominal 6 watts. And the next step, the next low-risk mission objective was to commission the camera. So that's something that Audie worked on. We'll chat about a bit more later. So we still have a lot more going on in the mission. We have next to commission and verify our attitude control system. So using the Earth's magnetic field to detumble us. Right now, we're just very slowly spinning. You can see that in the panel power graphs. And then we also have some more sensors on there that we have not turned on yet. As well as we have an auxiliary flight controller using some advanced, more advanced control systems. We have the 24 gigahertz transponder, which I'm sure you're very excited about. That's Paul's radio. And we have to fire the thruster, last of all, is Paige's propulsion unit.
How do you use the Earth's magnetic field to slow the spin down?
So, I can talk more about this when we talk about the controller, but the idea is that in low Earth orbit, you're low enough to actually measure and feel the effects of the magnetic field. So what you do is you use what's called magnetorquers. So it's just like electromagnets, basically. And as you excite the electromagnets, you get a force, you get the cross product of the forces of the Earth's magnetic field, and so therefore you're able to exert a torque on the satellite. And
Like pulse them on, or are they on all the time?
It depends on your control modes. We actually have, for safety, we have like a sort of permanent magnet simulation built in. So I know a lot of CubeSats do passive ADCS and they just have a magnet in there, but ours actually uses just a sort of basic control algorithm to sort of minimize the velocity relative to the Earth's magnetic field. So it is just like sort of a pulsed thing, but it's a very controlled pulse.
Right, okay.
And then, so just to add to that, so between the pulses, we have the magnetometer, which measures the magnetic field. So the whole intent is you want to generate a magnetic field such that you're providing a torque on the spacecraft that's slowing it down rotationally. So if you turn on the magnetorquers, then you turn them off, and then you measure the magnetic field, and you kind of just repeat that back and forth.
That's true. It does have to be pulsed, because otherwise it's very hard to accurately measure the field. So beyond that, so we've got these systems that contribute to this mission success. We've got COM2, again, the radio. We've got COM1. So we've got two communications units. COM2 rather, is the more experimental unit, and COM1 is the integration with AMSAT. We also have the ADCS system, kind of what we talked about, but with the addition of some additional sensors and the second flight computer, and the camera, which is an outreach payload with Raisbeck and Audi, as well as the power systems. That's the graphs that I was showing you earlier of the solar panel, power generation, power storage, power distribution, and then the propulsion unit finally on the bottom. And here is a more exploded view. So this is sort of the cool render of this with just a bit more detail. So the things that you can see here now are the patch antenna for the COM2 sitting on top. So I don't believe that's in that model, but it's here. We also have the ISIS dipole UHF VHF antenna. So I believe it stood for industrial system, something in solutions in space. Named quite a while ago, obviously. And so those are the antennas we're using. So UHF down, VHF up. We also have the AMSAT linear transponder, so it's both a communications unit as well as when we turn it over to AMSAT, it will become an amateur radio linear transponder. And like these are the magnetorquers here. These are the wound coils that you were asking about earlier that we can do that with. Also, our batteries, more on that later. We've got four batteries that get us a total of. I'll go into the specs when we get to that. Exactly here. So we're using the lithium phosphate batteries, which I believe those are the same batteries that were in the cell phones that were causing all those issues. Is that, no? Not quite. All right. They caused us some similar things, some shipping and testing and whatnot. So not exactly the same thing, but the thing that it does get us is it gets us a lot of cycles and it gets us a lot of storage, and so that's what the health of the power system is really what contributes to all the other sort of more high power payloads, like the thruster and COM2 and the camera, which is consuming a lot more power than sort of the nominal electronics. But our panels are doing quite a good job, even with the non-deployables. So with the deployable panels, you can face it towards the sun and potentially get more power, but even with the three sides of panels, we're getting a nominal 6 watts in the sun is over the whole mission is what we're doing. So here, this is sort of the actual satellite like you were seeing before. You can see the panels here with this sort of red, I don't remember what this compound we ended up using was, this sort of like red epoxy-ish.
RTV.
Yeah, like RTV as well as the render of the battery sitting there on the PCB and the stack. And so again, to the ADCS, so we have a V dot controller, which is basically minimizing your velocity, your V dot of the Earth's magnetic field, so detumbling effectively. We've got 3-axis magnetorquers. We have very full control, just not necessarily very quickly, as well as several MSP 430, just a TI MCU that comprise this more complex control system. And they talk across the CAN bus, which is a bus that I'll talk about a bit later. So we do have, like I said, the VDOT controller, and as I mentioned before, we can just basically simulate a permanent magnet ADCS system, so attitude determination and control system, as what most systems would use. It's just a passive to align you with the field. So in the case of the controller fails or something shorts, we can just revert to that mode. And to do that, we did a lot of hardware in the loop testing, because this is a control algorithm that was developed at a controls lab at the AA department of our school that we worked with. So we have this big old electromagnet right here, and we can, in very sort of we can swing it around, and so we can simulate the tumbling in the Earth's magnetic field. We can watch all the graphs on the computer and watch it try and actuate and slow that down. And in the simulation, then we can simulate the conditions of that. And there was a lot of work that went into that and verifying that that worked. So I mentioned the camera module, and I'm sure this audience is very excited to see this. It was an outreach payload through Razorback Aviation High School in collaboration with Adi and a couple other folks. I guess they're going to school. They're all in college now, but they worked very hard on this. It was a Raspberry Pi integrated with CAN bus rather, using a Raspberry Pi camera module. And we finally got some low-res pictures of the Earth. So we know vaguely that it's not flat, but not much else beyond that. Although I must say it does feel very cool to have built something that's gone up into space and taken such pictures. And thank you, Adia, for rendering these out of the data there. There you go. Yeah, we faked the satellite launch. So as you might be able to sort of glean a bit from this, we did more of like a decentralized architecture, so not fully distributed. I don't know if anybody's done that on a satellite. That would be cool, but I feel like impossible. But we have, the idea of this is that if there's rate events due to radiation failure or due to other factors, that certain systems can fail, we can just shut them off, and those won't affect the mission success of the others. So we have a total of 9 TI MSP430 microcontrollers. 2 Raspberry Pis, so one of those is running the camera and one of those is running Pulse radio. And we have 12 total nodes because the other node on that bus is the AMSAT COM1 unit. So over that communications bus, it's really resilient to radiation and disturbance. A lot of industry is using this, but I believe we're the first university to do so. So something more like I2C, we're able to use the CAN bus. We still have those on the satellite, but we're able to use the CAN bus as a fallback to potentially reset those in a very safe, very resilient way. And so yeah, like it's here, for instance, like we're talking about the magnetorquers, we're tumbling at a very good rate. So if something shorts in the controller, we're able to shut that off and potentially still achieve success on other things. I don't think that will happen, but that's part of the architecture here.
If that central node fails, all those other nodes around it are on their own.
Yeah, it's not a perfect system. So there are definitely single point failures. The idea is that you don't have as many single point failures, ideally. So we have like one sort of the power distribution board or the comms unit might be this sort of central node. So we have to build those systems very robustly, but then we can sort of take liberties or make it a bit easier, especially since this is like an undergrad development project. This also helps a lot with the element of getting students involved. Because if you have one very central system, like one flight computer that takes all the sensors and does all the actions, it's a lot harder to develop that hardware and software-wise. So now you can get even more undergrads on the team, develop cooler software. I mean, like with the outreach payload, is you can get more people involved, and that's just better for everybody with experience. But yeah, like you said, there's a lot of software precautions and hardware precautions. I know that on those central nodes, but there's fundamentally nothing you can really do about that. Maybe there's cool research out there, but nothing I've heard. So because it's rather modular, there's something that we can do that's really cool. So we start out with the sort of breakout boards of the components. Like here, this is one for our MCU plus CAN layout that's on all of the chips, or almost all of the chips except for the Raspberry Pis. But you have all these very modular boards that stack up on these rails as part of the final satellite. And you can kind of see that in this model. If you look through, they're just unpopulated boards. But we're able to actually take them apart and lay them out very flat in the engineering stages. So we have what's called the flat sat, and so those are just a whole bunch of boards chained together, electrically connected, just as you would in the full satellite. But if something goes wrong, it allows us to probe in there, like a UART probe or actually multimeter probe, as well as like swing the magnet over and do the hardware in the loop things. And actually, for the engineering models, we were able to spoof the sensor inputs, and so that really allows us to do a lot better testing there. And then eventually we move to the tower sat configuration, so more of a flight configuration. So we lose a bit of debug, but we're able to exercise our ground station, we're able to exercise operations that way. And finally, we do the final flight assembly with all the actual flight boards, seal it up, and then at that stage we're able to do just the final checkout and deliver it. Oh, this is a black stand, but. So we did lose a few things along the way. As you can kind of see, we have a few things, if you don't mind. So notably the deployable solar panels here, as well as the COM2 reflect array. So these are two deployables that didn't make it into the final version. So the key point being the reaction wheels. So reaction wheels are another way you can do attitude determination and control, or more accurately, attitude control. So that way you can siphon your rotational inertia to a wheel, and then very, very quickly, very accurately, if you do your controls, point your satellite. And so that a lot of our mission was sort of dependent on that. We were going to do velocity pointing, so pointing in the direction of our orbit. And so when you fired the thruster, it would very directly raise the orbit versus being more of a tech demo. As well as doing ground pointing for a very directional COM2 unit. And so unfortunately in our environmental testing and our vibe testing, thermal testing, we found that those wheels did not survive vibe. And so we could have continued with that, but it doesn't make sense to fly something that's potentially going to be faulty to the detriment of the mission. So because we lost the wheels, also the hinges bound up during that vibe testing, we found that they deployed, we reset them, put them through the vibe, and then deployed them again, and they just didn't deploy. So we had to scrap that. And so the COM2 reflector arrays in the same boat is if we don't have the exact fine attitude control, we don't want to have the COM2 be so directional that we'll never hear from it. Whereas now it's far less directional, and we'll be able to exercise that in the future. So this is all sort of the ground station work that I do, but the cool part that I mentioned earlier is that we have this whole ground station of AMSAT networks. This network of AMSAT ground stations that go to their central server, and so that way we're able to collect that data through FoxTelem and this ball aerospace software we use called Cosmos, and parse that data and use that to operate our mission on our ground station using everybody's network. And then from our station we have a single point of uplink. We can uplink, and a lot of our stuff goes directly onto the CAN bus. So it transitions very well from the development stage to the flight stage, because whereas we were plugged directly into the CAN bus transmitting on that bus, we now have an AMSAT communications unit. We worked with them a lot to get this functionality of just sending a CAN packet and having it being immediately on the satellite bus. There's a lot more there, but that gives you the sort of the gist of that.
You're saying they uplink as well, or just you guys uplink?
Oh no, so we are the only station that's licensed to uplink, and Paige did all the licensing, so if you have specific questions.
Sounds horrible.
Oh, we'll be talking at dinner.
So we are the only station that's licensed to uplink, but there are sort of two sets of commands. So we've got our piece that we developed sort of underneath theirs, and we can forward packets along our bus. We also do have commands that affect the operation of COM1, adjusting the transmit mode. That's pretty much all we do regularly, but just altering the function of that. But the rest of the packets just get forwarded across the bus. Again, that all comes through us. For now. Oh yeah, that's true. Until we turn it over to AMSAT, in which case it then becomes like an imagery transponder. So then that's just for the part 5.
That link is what's considered the sensitive uplink. So that link, people don't have access to that.
Right.
So the transponder is something else.
Okay, so the plasma thruster was the team that I led. I'll actually do a lot of the electronics work for it, but I did some of the early research for it. It's a solid fuel thruster, which is really good for things like CubeSats because they're usually secondary payloads. So if you're flying on something like the Cygnus capsule or going to the International Space Station, they really don't want you to have anything that possibly blow up. So commercial vessels are just right out. It's changing.
Batteries, we have to test the heck out of those batteries too.
So yeah, it's a simple and robust design, and it's actually been used on larger satellites going back as far as the 1960s for attitude control. Because they're pulse systems, you can deliver a tiny little precise bit of impulse and you tilt the satellite just a little bit. But because they're simple and solid fuel and robust, we thought it would be a good plan for being a propulsive CubeSat in space, and there's a lot of paperwork behind that anyway, but we got it on a flight. And so the interesting work that we did for the thruster, I guess first I'll tell you how it works. So there's 2 electrodes with a pulse plasma thruster, and you store energy at a high voltage across your main bank of capacitors. So we're looking at a kilovolt on 20 joules of capacitance. So we're operating at 10 joules of energy per pulse. At the distances that our electrodes are apart, kilovolt of voltage is just going to sit there. And so you need an igniter and then use a high voltage step-up transformer to basically seed electrons into there, and then they see this high electric field, and then they start the breakdown. And what happens when all this energy breaks down across the surface of your propellant is it ablates and ionizes some of that propellant. So every time you fire it, there's this little puff of plasma that comes out, basically. And we're talking about micrograms, tens of micrograms per pulse. So that's basically how it works. What we wanted to do with the thruster is to take it in a direction where we get a little bit higher thrust for power input, because that's something we're literally limited with CubeSats. You have these tiny little solar panel areas, and so you don't have a lot of power, and you typically, if you're in a low Earth orbit, you don't have a whole lot of lifetime. And so we wanted to increase the thrust output for power input, which is not usually what you're looking for in an electric propulsion system. Sort of the gold standard for previous things is your ISP is basically how fast your fuel is coming out. Because if your fuel is being exhausted faster, then you need less of it to accelerate to a certain speed. And so we took it in a different direction with our research, and that resulted in us going with, instead of Teflon, which is the fuel that's been used in the past, we ended up using solid sulfur fuel. And so we actually make molds of sulfur pucks that we put in the thruster, and that actually gave us about a 2x increase in specific thrust over the Teflon. So that was kind of a big win for us. And then we also ended up using, you can kind of see this, we call them daisy. It's a serrated geometry, which allows us to have a bigger surface area and still break down the same voltages. We did have, on the next slide, I have a model of it, but we did get it down to a 6U plus form factor. So this is 5 plus. This is about 5 centimeters, so it's half of one of those plus this is the technical term, is a tuna-can extension. And so that's where the fuel is, and that's where the nozzle is. I don't know how that got to be the technical term, but
all of the fuel is in that extension?
it is. So here's just what it looks like. So this is what it looks like all put together. This is our fuel puck. I think we have like 50 grams of sulfur, a little bit more than that. That all get stored, right in that. And that's another great thing about solid propellant. You have a high storage.
And about how many pulses can it in that fuel?
So no less than half a minute.
Okay.
So you have some pretty good life and pretty good control.
Yeah. So the original design, when we still had very big aspirations, was that we were going to raise the orbit with a maybe 50 meter per second LTV. And so that when we were still going to be able to point accurately for long periods of time, we were going to pulse it with high frequency, for like a third of the orbit for, once every other second.
And that raises it from what orbit altitude to what orbit altitude?
Not a whole lot. So it depends on what altitude you start at.
I'm sorry?
It depends on what altitude you start at.
And where at altitude are we talking about?
So we knew, we didn't actually know where we were going to get dropped off for a very long time. We ended up getting dropped off at 465 kilometers. So don't quote me on this because I don't know, but maybe it's in a couple of the proposals. But yeah, a couple
kilometers.
Tens of kilometers, I think. Yeah.
So this amount of delta V that this was designed for, it prolongs your mission more than anything. So normally, if you don't do anything, you're gonna come.
You don't decay, right?
Yeah.
So you're getting from about 450 kilometers up to maybe 480 or something like that.
A few low tens of.
Or
Or you keep it at 450
Yeah.
kilometers.
like for 10 years.
Yeah.
Yeah,
The
but you
satellite's
don't stay
probably
there.
going to come down in 3 years.
I'm sorry?
The satellite is probably going to come down in 3 years. just based off the amount of drag there is near Brent.
What happens is it's gonna burn up or?
Yeah. Except for the tungsten. It turns out if you're building a satellite, don't use tungsten. It doesn't burn up. So we had to go through, actually, this is one of the great things about going through NASA was they had like one of their official people do a big analysis to make sure that the tungsten wasn't gonna come down from too much energy, but it is gonna come down. Which is kind of scary.
Most of the Earth is ocean.
Yeah, exactly.
And when it comes down, people are gonna be excited about finding that.
Yeah, the little
In the
piece of
ocean.
tungsten.
They will, they will. They're,
Yeah.
yeah,
Uh,
just like hunting meteors.
It's true. So yeah, so the rest of the propulsion system all fits on these three boards. Our high voltage capacitors and our ignition coil are here, and then we tried, this is a very, very electrically noisy system. I mean, you're basically shorting
Yeah.
something.
Yeah. The spark gap.
Sparky.
And so,
Spark transmitter.
and so we tried to set it up in a way, which is why it kind of looks weird, where it's the only part where the boards go all the way out to the edge. Because we tried to set up basically little Faraday cages the whole way along. And so then we have our charging electronics are here, so this steps up to the high voltage, and this is the board with the microcontroller on it. And if this works, will it work? Oh, yeah. So this is a super, it's very, very fancy camera. The pulsing is an artifact of the camera, but that's a video of the thruster firing.
Real time?
Like, this has,
Be crazy high frame.
yeah, like I think you can get to 1 million frames per second, or like 1,000 frames per second or something.
Okay.
It's a high speed.
Yeah, it's a really, really fancy high-speed camera. So it's just kind of cool to see how they discharge.
And that was in orbit or down here?
Yeah, that was the.
Somebody stood behind it.
It's a great telelense.
Yeah.
Spacewalk and then they hung over.
Yeah,
That
that's
was
just
the
a
black
one.
and white.
Got their phone.
How far away were you when your iPhone?
Okay, communication stuff now. So there's COM1 and COM2. So COM1 is a radio provided by AMSAT, and then we purchased a commercial antenna, so that ISIS module. So that's a company where we just bought the antenna thinking that we're going to have a reliable system consisting of the AMSAT radio plus this antenna. And then everything else we build in the satellite, as long as we provide the power, then, we could, fail and we'd still have a beeper-sat. So that plan worked well, except for the fact that ISIS, that didn't come through as well as we thought it would. So we had some issues with getting an antenna that just didn't perform from an RF point of view. But we made it work. So we actually launched our engineering model of the ISIS antenna, which isn't ideal, but that got through. So a couple features. So this is going to be the first amateur satellite, I believe, that is a linear transponder versus just an FM repeater. So there's going to be an entire passband that essentially comes up on UHF and it comes down on VHF, and then there's going to be channelization within that band for
Not the
different
first.
users.
There's the CubeSat.
So okay.
Could be the first CubeSat, yes.
Okay. And then there's the telemetry downlink, which is a BPSK modulated downlink, and that's always continuously outputting. So right now there's stations picking that up. So that you can actually see in amsat.org/TLM. And then the program for that is this Fox telemetry. So it's an open source software, and then you can use, it's compatible with a lot of different radios. And then there's also an uplink, which we're using to command the radio a little bit to different modes, and then we forward cam packets. And then that's the basics with that. Any questions before?
It's inverted.
Yes. Yep. So the frequencies are.
My brain was trying to process
Sure, yeah.
840
It's like
to
lower
810.
It's like lower sideband, literally, it is.
Yeah, I understand. But it's inverted, so it hears high and transmits lows.
Yeah.
Sorry, yeah.
Here's what's high.
Okay, so when Paige and I started working on that lunar project, NASA was trying to promote development, technological development in propulsion and communication systems. So that's where, we had the PPT at the time, and then we started doing the communication work. So then and now, there's not really a good market for CubeSat high frequency communication stuff. So, and especially not like open source. So I started this project, and essentially it's a transmit only, and there's emphasis on the RF aspect. So I did as little as possible in the baseband, the low frequency. So the system works by having a Raspberry Pi 3, the DDR2 compute module variation, and then that goes to a V200 software-defined radio, which is, couple in, 2 by 3 inches, and then that's RX and GX. So I just pull just the GX off, and then that runs new radio to just give me around 2 gigahertz baseband. So then the RF front end up converts to 24 gigahertz, and then to 24.049 is the allocation, center frequency, and then it power amplifies it to about 1 watt. And then that goes to a 4-element feed antenna. So that feed antenna is shown here, just 4 little patch elements that are circularly polarized. And then the reflector array, maybe, I didn't put a picture, maybe we'll go back.
Yeah, there's one in the way back.
Yeah, maybe.
Is the W on the reflector array part of the secret sauce that goes into the antenna?
Unfortunately not. So the 4-element. Well, I still was printing it.
Yeah.
So University of Washington did not like us putting a logo down in places, which was this is a 4-element feed, and it's a 4-element feed because it had the right beam width to be a feed to then this reflector. So the reflector array works like a parabolic dish. So a parabolic dish uses the geometrical distance from the antenna reflecting off of the parabolic surface and then heading straight out. So this surface has a ground plane, and then it has these little metal elements. These little elements essentially can accept and then retransmit the signal from the feed, and then depending upon the rotation, the outgoing phase can be controlled. So just like a parabolic dish, the feed illuminates the surface, and then it constructs an outgoing beam in whatever direction I want, which in this case is just flat parallel to that surface. So when the pointing of the spacecraft went down without the reaction wheels, this feed antenna was essentially just brought to be flat, and that was just removed. But that was kind of the initial scope of this project. And then the nice thing about the reflector is it scales really, really nicely. So the intent was to develop a framework for using just FR4, so this can be printed in China for $1 basically. And then these substrates here. So this is just a Rogers substrate, and it's a student. Rogers just throws you things for free. And then having this cut out with, by a laser by a guy in Capitol Hill, metric straight space, $200 or $200, whatever it is. So it's really inexpensive. There is the ANSYS tool, which as a university student I have for free, but you don't really need ANSYS to even design something like that.
So that thing's entirely passive then?
This part is fully passive. So the nice thing about, the advantage of reflector arrays versus fed antennas, like typical big phased arrays, is you don't have the losses from the feed network. So you essentially have like the feed coming into this antenna, but those can be pretty efficient. You usually have like big losses if you're going to hundreds or thousands of elements,
Especially 24, right?
Yeah, unless I guess the new practical approach is to do like PAs everywhere and just behind the elements. But low cost was the goal there.
Power too.
Yeah, so that doesn't impact your power budget, right?
Yeah. So fitting within the CubeSat form factor, and then power budget, and then cost. So those are kind of like the top level mission goals, and then kind of having a system that could actually adapt in frequency. So all like the RF chain can go all the way into the NASA what they call K band. So it's like the 25.5 to 27 gigahertz for the near space for NASA science missions.
The little dots you had on there with the slots in them look like? That's what I was seeing, right?
Yep.
Is there a name for that configuration? I haven't ever seen that.
I mean, just like double slotted rings. I mean, yeah, there's different names, like that specific type of reflecting element. So that does actually take a lot of emphasis in building, to get that tuned right, but that's not particularly novel in this, that's already been developed. So there's different types of resonating elements. The simplest would just be a square patch. You're essentially changing the resonant frequency of the patch, and that in fact changes what the outgoing phase is. The nice thing about the circle elements is you have full phase control, 0 to 100 or 0 to 360, whereas if you do a linear patch, you don't have the full swing. And then circularly polarized helps coming through the atmosphere. This is a stock-up of what's inside of this. So this kind of has, the top board is the RF board, so that gets its own chamber on the top, and then above the board there's just an RF absorber. So I don't think I included it, but one thing here was a microstrip bandpass filter, and that's going to radiate. So in the RF chain, of course, like harmonics are a huge deal, so putting filters in and getting your output spectrum to be clean was an emphasis that I was working towards. So then underneath, so everything below this top PCB is in this bottom chamber. So the idea there is like, let that be noisy if it is, because it has a digital pressure refinement and whatnot. And then this whole hunk of aluminum acts as a heat sink. So the unit cannot stay turned on indefinitely. It will overheat. So there's a timer, and the power budget doesn't support it. So it operates for some amount of time. The components within that RF front end, generating everything before that PDA is like a few watts. So it's quite difficult. Most of the parts are just like from analog devices. They're the old Hittite, if anyone's familiar with that, analog devices back then. But it's power hungry. So I think that's, everything I have.
Okay, but we didn't talk about data rate. So so it looks like 50 megahertz bandwidth?
Data rate.
And data rate is?
So data rate is, so it can transmit sine wave and then increments of BPSK, just encoding a simple, hello world type message. It has on board the capability to do 1 megabit per second. But the ground station for that link budget, we don't have the resources to ever be able to point something that accurately. So initially, we talked about the kind of the D-scope efforts here. We also had, a larger dish and a 1 degree pointing accuracy. It is an alpha spin rotator. And we had problems with it, which is not completely uncommon. It would just flake out on us.
You can set it next to mine.
So we ended up, going to the G5500 rotator, which is really bomb, and doesn't have good pointing for this need. So yeah, when it comes to higher frequency stuff, pointing and then calibration of that pointing is really challenging. And at the university level, like, those aren't resources that we can easily get.
So 50 megahertz, that's what I'm saying?
No, so that's with all the filters. I mean, yeah, if you got really clever, because it has a B200, that's what it could do. But we're only allocated 24.049 gigahertz center frequency within a 1 megahertz.
1 megahertz. Okay.
Gives you that.
So just sort of in summary, here's a couple things that we think are pretty cool about this satellite. Number one, we've got the COM1 module built by AMSAT. That's the first AMSAT integration for university partnership. As far as we're aware, we're also the first university level CubeSat to fly CAN bus, which is, like I said, is pretty common in industry, and it's just a bit more resilient way to do it. We're the first satellite built by university students in Washington State. I mean, that's what people like to report on, I guess. I don't know. But also, almost everything except for the commanding software is open source. So all the flight software code that I worked on, all of the controls code that does the ADCS is open source in another repo. All of the PCB designs, whether it's Pulse Radio or others, just not the AMSAT side of things, are all on that repo as well. All of the ground station software, using like extending the Ball Aerospace's Cosmos, all that config is also open source. And you can find it here at our team at CubeSat. So people seem to be very interested in Pulse Radio, and you can find some more stuff up there. So we don't just do satellites. So this was just, we wanted to focus on this mission because we think it's very cool and interesting, but we wanted just to highlight the fact that we have a lot of very talented undergrads, and we have a lot of other work that we do. So we do like high altitude balloons for testing on the PPT, but otherwise testing our software equipment and some ADCS sensors and things, but also just to get people good experience when we have, you know, like legal times on this, when all the work is just, okay, sit down and fill out the paperwork. Now we have all these talented undergrads, we can keep them going on things. We're also doing a suborbital payload with Blue Origin. So Blue Origin is contracting with NanoRacks to do. So like Paige mentioned, the structure of the CubeSat is very it's very highly specified. So there's all these sort of intermediary companies that are hosting CubeSat launches, even for non-satellite. So this is just a pure suborbital launch to test their new Shepard rocket. But because of that, they're flying a 2U form factor payload. It's not going to go into space, but you're able to get power and run experiments and things. And so we actually have a lot of folks in the lab that had to miss a meeting for to come here that are working on doing electroplating in microgravity, which is actually a very not very well understood field. So it's really cool to break even more ground there. As well as for HuskySat-2, well, we just got one up, but we've had a bit of time to think, and we're currently in the design and proposal stage for that. So we're currently just fleshing out our proposal ideas, getting out there, getting funding, but also like looking for members and sponsorships to get that project going. Because currently the biggest hurdle, I think, is getting a launch. Because as for a satellite, that even at a CubeSat university level, that's something that requires grants. I mean, it's not something you can. I believe somebody suggested putting together a bake sale, but I that'll work. So that's what we're doing now, and just keeping those undergrads involved. And what that results in is we have our alumni working at. I just picked like the top third of our roster to put on here. But you know, coming out of this, we have folks working at even Microsoft. I saw it. I picked that from somewhere else in the roster. I wanted to throw that up there. But just coming out of the lab with all this great experience, PhD level undergrads, just doing this hands-on, and I mean. The focus was on the science, but also the focus was on being an outreach and undergrad like an engineering and research opportunity. I think for that, I think we've succeeded. So, do you have any questions?
Yeah, a couple of them. First one has to do with cryptography. Do you encrypt the command and control information that goes over the radio waves? And then the second one has to do with solar phenomena. So pick whichever one you want to talk about first.
So just sort of what kind of encryption we have?
Right, if any.
Yes, no, it is uplink is encrypted, and that is dealt with by MSAT. Maybe Paul knows a bit more about that, but I don't think we can discuss everything to do with that.
It's encrypted, and our downlink is completely unencrypted. So you can actually go to the repo and get Cosmos and decode our data beyond what Fox. So Fox telemetry will decode data that it collects. So it actually it's connected to our CAN bus, but it also pulls in analog lines. So we thought, okay, if our CAN bus dies somehow, we're going to still get some diagnostics from the spacecraft. So we actually have, white wired in lines. So everything in Fox telemetry is from COM1 in that fashion, and then Cosmos is what gets what processes everything else.
Cool. Yeah, so like I mentioned with the sort of the two systems almost is, so Fox telemetry deals with the AMSAT side of things, so getting their telemetry in a very human readable way. But there's all other kinds of specifications to parse our data and set that out. But it's all open source again, so it just requires a bit of extra work. And what's the other piece?
Solar phenomena, like shielding and how you protect against solar radiation.
Yes.
Coronal mass ejection, solar winds, all that fun stuff.
So yeah, we've had we're aware of that. But the deal is with a lot of our controllers, we're very cognizant of what we put in, like NVRAM basically. So we know everything. If random bits get flipped, at least on our side of things, we have very fine control over what we can reset, what states we can recover from, and being very controlled about that. I mean, fundamentally, we're not really flying anything that's rad hard. So there's only so much we can do, but although we have taken some software precautions for that.
So we are using the FRAM variant of the MSP430. So FRAM is naturally radiation resistant. And then additionally, we have, so the the lowest level brain, the distribution MSP 430, essentially it will shut anyone off that pulls too much current, and then it itself has a little overcurrent protection. So we're protecting against latching of individual subsystems as well. So maybe we can't get the catch the latch such that we save that item, but the idea is if something latches, it doesn't take down the whole vehicle.
And even if there's an issue with the CAN bus, that's sort of the distribution board's job to deal with that, and it'll detect that something's up and do our best to rectify it. I mean, fundamentally, we have enough of that. There's nothing we can do, but I mean, we've certainly taken some precautions in that regard.
Yeah, I'm impressed you can do it with.
Pretty friendly orbit. It's not like solar winds really affecting us. Mostly, we've seen 2 resets over the whatever anomaly. On space.
Yes, we have seen resets.
3 resets.
So there's resets on, so there's COM1 resets, but there's also resets on our side.